Hello everyone. Today we discuss the homomorphism of ring. Already in our last class we have discussed this topic and some properties. Okay, so let's have a look quickly. Okay, so what is homomorphism of rings? Basically, you have a ring, okay, and from that ring to you have another ring r dash. You have a map from r to r dash, okay, but with some special property, right? That basically phi of a plus b will be phi a plus phi b, right, for all a b belongs to r, and one more property that a dot b equal to phi a times phi b, right? So if this two property satisfy, then we call this is your homomorphism, right? This definition already you have noted earlier, right? Now if you add homomorphism plus injective, that is called monomorphism. Homomorphism plus surjective, that is called the epimorphism. And if it is bijective plus homomorphism, then it is called the isomorphism. Okay, so this is already we have noted down earlier. Okay, and if you consider some example, for example, if you consider the map f from z to z by f of x equal to 2x, okay, so if you try to think about these two properties, so this satisfy both the property, okay, and is it one to one? So you will get obviously it is one to one, right? If you do fx equal to fy, so this imply 2x equal to 2y, so this imply x equal to y, so this is one to one, so therefore monomorphism. Is it on to? So obviously it is not, because you can see in this set 3 belongs to in that set, right? 3 belongs to this, but is there any x for which your fx equal to 3? So answer is no, so that's why this is not onto. So this is just monomorphism, right? Okay. Another example, if you think about the map z to z such that fx is equal to minus x, okay, so you will see this does not satisfy the property in this one, okay, so that's why this is not a homomorphism. So this type of thing already we have discussed. Now whenever you have homomorphism, there this satisfies some property. For example, if you have the additive identity 0 here, so that will map to the corresponding additive identity of this map, okay, and if you have a multiplicative identity I, so that will be mapped to the corresponding unity phi of I, or you can say I dash, that I dash will be your phi of I, okay, and this will be your phi of 0, that type of thing, okay. So additive identity and multiplicative identity map to the corresponding thing in the R dash, okay. So this type of proof are very easy. If you are facing any issue, you just send me in the WhatsApp, okay. So I'm not going to prove this type of thing, okay. And there are some other result, like if you have a phi of minus a. Okay, so that will be your minus of phi of a, right? And if you have a unit element, a is a unit, a is unit, then if you do phi of a whole to the power inverse, so that will be actually phi of a inverse. Okay, so this type of thing. Okay, so this proof are very easy, you can just have a look. Okay, now after that we have defined some set, like what is the kernel of the map, like what is defined by car phi. Okay, and another thing is your phi of r, which is called the homomorphic map, right? So you know car phi is a subset of your the domain set for which the phi map to the 0 element, right? So if this is phi, so basically inside that set you are getting some car phi set which maps to the here the 0 dash element. Okay, and the whole set is contained in the set. Okay, so that set is actually called the phi of r, because if it is epimorphism, so then actually you will get the whole r dash, right? So this is like the this kernel, I think, concept you have learned in your linear algebra courses. So there also you have that car of t, image of t, that type of concept. So this is the similar concept. Okay, and later on you will able to prove that this car phi will be a ideal of this r. Okay, okay, so let's have a look some theorem. For example, if I do this one, theorem 3.14.3. okay, what is this theorem? So let r and r dash be two rings and phi r2 r dash be a homomorphism. And then phi of r is a subring. That means this phi r will be a subring of the r dash. Okay, so what you have to prove a set is subring? So you know that you have to show the 0 element, and if you consider 2 element, they are addition and they are basically subtraction, and their multiplication should be in that set, right? So obviously your 0 dash equal to phi of 0, phi of 0, that only belongs to your phi of r, right? So 0 element is no issue. Now just consider 2 element. Let a dash and b dash belongs to phi of r. Okay, so that means there exists a and b belongs to r, for which are such that phi of a is your a dash and phi of b equal to b dash. So if you do a dash minus b dash equal to phi of a minus phi of b, right? So this is equal to, you can write phi of a minus b. So you see, if your A belongs to R, B belongs to R, so A minus B belongs to R, right? So this is belongs to phi of R as A minus B belongs to R. Okay, so this is already proved. Okay, and you have A dash into B dash, so this is equal to, you write phi of A into phi of B, so equal to, you can, using the homomorphism property, you can write this, and this is equal to, you can write phi of R as A into B belongs to R, right? So you prove the two things, so you can say phi of R is Subring. Okay, okay, in the similar way you will able to prove that. So this is already you have seen, right? So similarly you just have a look on the theorem 3.14.5. okay, so what this theorem says, actually you just know the concept. So R to R dash, so if you have a subring S which is a subring of R, okay, so then you will get some phi of S, right? So this phi S actually also be a subring of R dash. Okay, this is your part 1. And conversely, if you have a subring S dash, okay, S dash is a subring of your R dash. Okay, so if you come back to the inverse image, right, with the map phi inverse, okay, so then actually you will get this is also a subring of R. Okay, so this type of thing you just have a look. Okay, now there are some other theorem. For example, if your R is commutative, if your this set is commutative, so then you will get this is also commutative. Okay, so these are very easy to prove. For example, what you have to show for commutative, basically if you multiply with two element, right, it doesn't, obviously you know the ring is commutative with respect to multiplication, because additive whenever you are doing, so always you have that commutative property. Anyway, so whenever you are doing multiplication A dash into B dash, so you will write phi A into phi B, right? So using that you have phi of AB using homomorphism property, and since your R is commutative, so you can swipe, right, B into A, so after that you can break. So these are very easy, just have a read. Okay, so this is your actually theorem 3.14.4. okay, okay, so in case of subring, whenever your map is homomorphism, that's it. So you can have a look this theorem 3.14.3, 14.5. so this is for subring. But whenever you are doing deal with ideal, so your map should be onto. Okay, so this is very very important. For example, theorem 3.14.6. so let R and R dash be two rings, and phi R to R dash be an onto homomorphism, then I am proving only the first one. So if U be an ideal of R, then phi of U is an ideal of R dash. And similarly the second one, if R dash be an ideal of U dash be an ideal of R dash, then phi inverse R dash U dash is an ideal of R. So what is the difference between subring and ideal? You see, you require the onto condition extra. Okay, so I am proving the first one. So obviously ideal also is subring, right? So your phi u is a subring, you don't have to prove, right? So since u is a ideal, therefore ideal of R, and therefore a subring of R. Okay, and phi of R, therefore phi of U is a subring of this is done. Okay, now what you have to prove for the ideal property, that if you take any element from that ideal, for example A, and if you take any element from the ring, then RA should be in that ideal, right? This is for any, and this is for actually left ideal, and conversely you have to show AR. These two things should be inside that thing, then that will be proved this is ideal. I am doing the first one, okay, only. So phi u, you have to show this is a ideal of R dash. Okay, so what you have to take, you have to take any arbitrary element from the phi u and R dash from the ring R dash. Okay, so let A dash belongs to phi of u and R dash belongs to R dash, right? So then there exists A and R belongs to, there exists A belongs to U and R belongs to R. This is why this is exist, because this your onto, otherwise it will not exist. This is always you can say, because you are belonging to phi of u, so obviously there will be some A for which phi A equal to A dash, right? But this R, this exists only for the onto one. Okay, so this is you have. So what you have to show, A into R and R into A, both are belonging to the ideal. That's it. Okay. Now your U is an ideal, right? U is an ideal. Now U is an ideal, so you can say R into A and A into R belongs to U. Okay, this is you have. Now for the for showing your phi u is a ideal, so what you have to show, now R dash into A dash. So this is, you can write phi of R into phi of A equal to phi of RA. So this is belongs to phi of u, and similarly you can show So you show the both way. So in this way you can show, right, phi of u is an ideal. Okay, so this is done. So now you just think the second part using your 3.14.5 second part. Okay, so similar way you have to do. Okay, now the next thing, this is also important, theorem 3.14.7. okay, that car phi is a ideal of R. Phi, you have a phi R2 R dash be a homomorphism. So that car phi is an ideal of R. Okay, so what you have to show, basically the same type of thing. You just take a arbitrary element from that set. For example, you just take a from the car phi, okay, and take R from the main group R, right? Then you able to you try to show that R into A and A into R belongs to car phi. That's it, right? How you will able to show this thing? So what is the definition of car phi? Car phi definition already you have note down in the note, right? Basically, if you apply the phi of that element, you will get zero element. So you just do, if you have taken A belongs to car phi, this means what? Phi of A is your 0 dash, right? And so here if you do, what is your phi of RA? So this is your phi of R into phi of A, since your phi of A is 0, right? 0 dash, so you will get 0 dash. So what this imply? This imply your RA belongs to car phi. Similarly the opposite one. So these are very easy. You have to understand what is the logic is going on. Okay, okay, this is important. You can skip the 3.14.81. you just focus on 3.14.9. okay, let R and R dash be two rings and phi R2 R dash be an onto homomorphism. Then phi is an isomorphism if and only if car of phi is your singleton zero. This is important. Okay, okay, so if you assume your phi is a isomorphism, so if you phi is a isomorphism, then phi is your 1-to-1, right? Then phi is 1-to-1. So you know phi of 0 equal to 0 dash, right? So 0 is the pre-image of your 0 dash and this is 1-to-1, right? So using the 1-to-1 property, so what you have in the car phi, car phi you have only this element. This is easy. Now converse part. So you have already phi is a 1 2. So what you have to show? Only the 1 to 1, right? So for 1 to 1, what you have to do? You have to take two element phi equal to phi b. You have to show a equal to b. That's it. Conversely, let a and b belongs to R such that phi a equal to phi b. So in converse part, basically you have car phi equal to 0, that you know, right? Okay, now if you take in one side, this is you have to write 0 dash because this is in your R dash, right? Phi. So from there you have phi of a minus b equal to 0 dash. So from there what you will get? A minus b equal to 0. As why? Because car phi, you know, car phi is equal to only 0 element. So a minus b should be 0. So from there what you are getting? A equal to b. So phi is a 1 to 1. Okay. This is fine. Okay. After that you have some result that RBA commutative 3.14.10. Okay. So you just have a read that if your R is a commutative ring, then R dash will be also commutative. This is actually earlier result, and this is for isomorphism. So isomorphism, you know, if you have all the thing will be same. Basically there is some notation also. R and R dash will be isomorphism, then you can write this type of thing, right? Okay. Okay. Now after that you have now we move to the next theorem. Theorem 3.14.11. Okay, these are very easy, but let's have a look because this is required for the fundamental theorem ring homomorphism. Okay, so let U be an ideal of R and theta, which is a map from R to the quotient ring R by U. This is well defined, right? Because U is ideal, and quotient ring concept already we have discussed earlier. Defined by theta of x equal to x plus u, right? For x belongs to R, is an onto homomorphism. With kernel u. Okay, so okay, x belongs to R, so that this is you have to prove basically, so that theta is an onto homomorphism with kernel u. Okay, so how to prove the onto? First you have to show homomorphism. Okay, then you have to show that car of that will be your u. Okay, so for homomorphism proving, you just show that theta of x plus y equal to theta x plus theta y, and your theta of xy is equal to theta x in theta y. That's it, right? So let x and y belongs to R. Okay, then obviously theta of x, your x plus u, and theta of y will be y plus u, right? Now then theta of x plus y will be x plus y plus u, and using the quotient ring property you able to break this, right? So this is equal to theta x plus theta y, and your if you do for theta x into y, this is your xy plus u. So this you able to break with this. Okay, thus theta is a homomorphism. Okay, so what will be your car of theta? Car of theta is your what? For all x belongs to R, such that theta of x will be, what is the zero element of your R by u? Only u, right? So this imply x belongs to R, such that x plus u equal to u. So when this is happening, whenever your x belongs to u, right, that means your the whole set u. So this proves your car theta equal to u, right? And this is by default onto, right, because with the R by u element will be itself your x plus u. Okay, so this type of map, this theta map, this is actually note, this theta map known as natural homomorphism. From R to R by u. Okay. Okay. Next one is very important. Sometimes it is may ask that state fundamental theorem about ring homomorphism and prove it. Okay. So next one is your this one, that fundamental theorem of ring homomorphism. What is this theorem says? Let phi be a homomorphism of a ring R onto a ring R dash with kernel u. Okay, so basically R to R dash you have a map with the kernel u. Okay, then R dash is actually isomorphic to your R by u. This is you have to prove. Okay, this is actually isomorphic image of this. Okay, so here basically you have to use the natural homomorphism map, because you know that R to R by u you have a natural homomorphism, right, that will use. Okay, so we are defining another map. So how to prove? So let so basically whenever you have to show this is isomorphic, so you have a map from here to here or here to here. Anyway, that map should be homomorphism, one to one and onto. If you satisfy all the thing, then this is done, right? So you are defining a map. So let us define a map this is little bit constructive also. Psi map you are defining from where to where, r by u to r dash, you are defining in this way, defined by by what is the thing, how this element looks like, psi of a plus u, right, equal to, you will get that your earlier map, that phi map from r to r dash, so that map. Okay, so you know that you have a map from r to r dash, right, and where this if you consider element a plus u in that questioning r by u, so where this a lies, from the r, right, so that's why phi of a should be in your r dash, so that's in this way you are defining. Okay, now you have to define that this map is well defined. Okay, so what you have to show for the well defined, this is actually the opposite part, your one to one part. Basically, if you consider x equal to y, you have to show phi x is equal to phi y. Okay, this is what the well defined. And whenever you have to show one to one, so phi x equal to phi y, you have to show x equal to y. Okay, so here we have to show all the thing, right, because you have to show this is isomorphism. Okay, so well defined. So for well defined, what you have to consider, you have to consider two elements, right, so let a dash plus u equal to a plus u for some a dash and a belongs to r. So if you so what you have to show, psi of that thing, right, psi of that will be psi of this. Okay, okay, fine. Then okay, this imply what, a dash minus a belongs to u, right, because you know earlier you, if you have a plus u equal to b plus u, so if you have, then you can write a minus b belongs to u, so using that what you have, so from there you can write phi of a dash minus a belongs to what, this is belongs to phi of u, right, and u is the kernel set. This imply phi of a dash minus a equal to 0 dash, right, since phi of u is kernel, actually u is kernel of phi. Okay, so if you break this thing, phi of a dash minus phi of a equal to 0 dash, that means phi of a dash equal to phi of a, that means your psi of a dash plus u equal to psi of a plus u. So this is done, right. So this is your well defined. Okay, now you have to show homomorphism. Okay, so for the homomorphism, what you have to show, if you take two element, okay, so you have to break that. This will be psi of a plus u plus psi of b plus u. So these are easy, you can easily prove using the quotient ring property. So from there you can write this is your phi of a plus b, and this is equal to, since phi is a homomorphism, so this will be used here, right? So from there you are getting psi of a plus u plus psi of b plus u. So this means this is done. Now you have to show another multiplication one, right? So this is using the property of your quotient ring. You have ab plus u. Now this is your phi of ab. Now using the phi is homomorphism, so you will able to break this. So this is equal to, you can break as psi of a plus u into psi of b plus u, right? So psi is 1 to 1. Okay. Okay, so this is psi is homomorphism. Now you have to show 1 to 1. So 1 to 1, what you have to show? Let psi of a plus u equal to psi of b plus u. So from there you have to show actually a plus u equal to b plus u. Okay, so from there what you will get? This is equal to phi a, this is equal to phi b by the definition, right? So from there you are getting what? Phi of a minus phi of b should be 0 dash. So from there you are getting phi of a minus b, this is equal to 0 dash, right? So from there you can say a minus b belongs to u, since u is the kernel, right? Is the kernel. Now whenever a minus u belongs to u, so from there you can write a plus u equal to b plus u, right? So psi is 1 to 1. Okay, and you just have a look. This is your on to also, because all the element is looks like your phi of a form, right? So on to each element of R dash is of the form phi of a. For some a belongs to R, right? R, and since the pre-image of phi a is your a plus u in R by u, because u is the kernel, right? So every element of your R dash will be, you have phi of a form. You don't have any other element. Okay, so it is satisfying all the things, so that therefore psi is an isomorphism. Psi is an isomorphism. Okay. Okay, so this is your complete part, and after that you just do the worked example 3. Okay, this is your right. Basically this is says if you have a map from Z to Z, some isomorphism, then you have only the phi x is equal to x, the identity transformation. You don't have any other map. Okay, so this is, you just have a look. So this is your full part of your homomorphism chapter. Okay. Okay, bye.